we analyze extrema, we're going to have some very important terminology or vocabulary that we need to be comfortable and familiar with. The first word that we're going to look at is what is a critical number or a critical point. So F needs to be defined at C for us to have a critical number. So we're not talking about a discontinuity, we're talking about something that actually has a value, but the derivative at C could be 0. That's going to be a horizontal tangent. And we've done that analysis quite a bit. Or F could be not differentiable. And another way to think about F not being differentiable is to think about F prime of C is undefined. So if F prime is equal to 0, or if F prime of C is undefined, but still having a value, right? So we're talking about a cusp, a sharp turn, perhaps a vertical tangent, but not a discontinuity. Then at C, we call that a critical number. If we list it as the XY ordered pair, we call that a critical point. It's important that we distinguish the difference between those two, even though the difference is pretty subtle. There is a difference between a critical number and a critical point. Now, why is this critical? Why is this important to what we are doing? It is a critical thing. It's because of this theorem. And this theorem says that relative extrema occur only at critical numbers. So if I want to analyze relative extrema, I'm going to have to first start with what are the critical numbers of that function. So that's a big deal. Now let's talk a little bit more about absolute maxes and mins. Whenever in this example, or in this question that they're asking me, it asks to just name the max and min. We're talking about absolute maxes and mins here. If it doesn't define relative, it's talking about the absolute. So the maximum and the minimum. Notice that all these graphs are really similar. The only difference is going to be these holes, right? And we're going to look at how that changes how we analyze the function. So first thing is I'm going to assume that this is the point -1, 2. I'm going to assume these are integer values. And then I'm just being asked, what is the minimum? Well, this minimum is the lowest value on this function. So the minimum is going to be at the point 0, 1. Now, even though that's also a relative extrema, because relative to the points around it, right, relative to these points, this is the lower point. It is the absolute minimum because it is the lowest point on the closed interval. Now, the maximum is an endpoint. So remember, absolute maxes and mins could be at a relative extrema, or they can be an endpoint. But these are absolute extrema here. Right? So this is going to be at a relative also. Okay, and then this is going to be at an endpoint. So just something to consider. Now, minimum here is going to be a little bit different for B. I'm sorry, not the minimum. The minimum is going to be the same. The maximum is going to be a little bit different because this endpoint is now a hole. So I don't really have an endpoint. Well, what's my absolute maximum? I can't get close enough here. I know it's really close to 2.5, but I don't have a specific point that I can say that is the maximum. Now, this looks like it might be considered a relative maximum, but for the purposes of our class, we're never going to call an endpoint a relative max. Technically, relative to the points around it, this is higher, but because it's an endpoint, we're not going to label it as such. Okay, endpoints are kind of their own little world, and they've got some nuances to them, so we're going to be really careful around endpoints. Okay, but the minimum I can define. The minimum's at 0, 1, but I don't have a maximum that I can actually define. Now let's look at C. Again, that looks like it's going to be the minimum, but now I don't have a value there, so I don't have a minimum, but I do have a maximum. So the point of all of this was to recognize that in order for me to guarantee that there is a maximum and a minimum, the function has to be on a closed interval. If the function is not on a closed interval, then we're not guaranteed to have a maximum and a minimum. We might, but we're not guaranteed that. So we're going to say function must be defined on a closed interval. We're going to circle that word guarantee. Defined on a closed interval. Now, the point of all of this is to lead up to this extreme value theorem. Now, we've already talked about intermediate value theorem, so that was the first theorem that we really kind of dove into. Extreme value theorem kind of has some similarities. It's not near as complex, but it's definitely talking about this analysis of the function. And the idea is that if f is continuous on a closed interval, right, it has to be a closed interval, then f attains an absolute maximum and, this should be the word and an absolute minimum on the interval from A to B. And those numbers technically could be the same. Okay, I can have the same min and max if it's a horizontal line, which is crazy to think about. But if I have a closed interval, then the absolute min is the same as the absolute max. But I have an absolute min and max as long as we're on a closed interval. So that is extreme value theorem, and we need to be familiar with that.